Let's look at some least squares problems. So in this video, I'll tell you what a least squares solution is, and we'll take a look at some interpretations and some examples. So suppose I have an m by n matrix A and a vector B in Rm. So first, the definition: a least squares solution of the linear system Ax equals b. This is a vector x hat in Rn that has the property that the length, or norm, of b minus ax hat is less than or equal to the length of b minus ax for all x in Rn. So this length of b minus ax hat, that's the distance between b and the vector ax hat. And similarly, the length of b minus ax is the distance between b and the vector ax. And what we want in a least squares solution x hat is that the distance between b and ax hat is less than or equal to the distance between b and ax, where x ranges over all vectors in Rn. So let's take a look at a picture of what that looks like. So here's the column space of A, and there's my vector b. So ax hat is going to be in the column space of A, right? Because A times x hat is just some linear combination of the columns of A. It's this vector I've drawn here. And I want the distance between B and ax hat to be as small as possible, right? Because this has to be smaller than the distance between B and ax for all x in Rn. So I want this vector from B, this distance from B to ax, to be bigger than or equal to the distance from b to ax hat. So by the best approximation theorem, a least squares solution then has to be a solution to ax equals the projection onto the column space of A of the vector b. Right, so here this ax hat is actually equal to the projection onto the column space of A of the vector b. And so let's call that vector b hat. We're going to call it b hat just to simplify the notation a little bit, and we'll try to figure out how can we actually compute the least squares solutions. So suppose ax hat equals b hat, then b minus b hat is in the space, the orthogonal complement of the column space of A, right? So it's in the column space of A perp. That tells us that b minus b hat is in the null space of A transpose. That means that A transpose times b minus b hat equals 0, which tells us that A transpose times b minus ax hat equals 0. Now let's just multiply that out. That says A transpose B minus A transpose A times x hat equals the 0 vector, which tells me that A transpose B is A transpose times ax hat. Now this equation, A transpose A times x equals A transpose B, this is called the normal equation for the linear equation ax equals b, right? And so what we see is a least squares solution is actually a solution to the normal equation. Right? What that means for us is if we ever want to find a least squares solution to ax equals b, what we're going to do is just solve the normal equation A transpose ax equals A transpose b. Right? What does that mean? Well, that means we multiply A transpose and A together to get some coefficient matrix. We multiply A transpose and B together to get some vector. We set up the augmented matrix for the normal equation, and then we can row reduce to solve. So let's take a look at an example. Suppose A is this matrix whose columns are 2, minus 2, 2, 1, 0, 3. And B is the column vector minus 5, 8, 1. We want to find a least squares solution of ax equals b. So we need to find the normal equation, A transpose AX equals A transpose B. That means first compute A transpose A. So A transpose has as rows the columns of the matrix A. So its first row is 2 minus 2, 2, and second row is 1, 0, 3. And I just take that matrix A transpose and multiply it by A. If I do the arithmetic, I'll get this 2 by 2 matrix, 12, 8, 8, 10. And so notice, this matrix is symmetric. It's equal to its transpose. And this is going to be true whenever you compute A transpose A. And so if you ever get a non-symmetric matrix out, then you need to go back and check your arithmetic. Okay, so next I compute A transpose B. And I do that matrix vector product. And when I simplify the arithmetic, I get this vector minus 24 minus 2. And so the normal equation is just given by 12, 8, 8, 10 times x equals minus 24 minus 2. So I can solve to get the least squares solution. So let's set up the corresponding augmented matrix, and then we can just row reduce. All right, so there, I've row reduced this thing down, and I see that x hat is the vector minus 4, 3. That's the least squares solution. So a few closing remarks. One, the least squares error is just the difference between the vector b and the vector ax hat, right? And so that's that that bit that we're trying to make as small as possible is the vector b minus ax hat, and so its length is called the least squares error. Two, if the linear system that you're trying to find a least squares solution for is actually consistent, then the solutions are exactly, the least squares solutions are exactly the solutions of ax equals b, right? The difference now, is if ax equals b is inconsistent, meaning it has no solutions, the least squares solutions are still going to exist. They're essentially the best we can do to solve a linear system, even when it's not solvable, when it doesn't have a solution. Three, if the columns of the matrix A are linearly independent, then ax equals b is actually going to have a unique least squares solution, right? And that's what happened in the previous example we were looking at.